This video will provide an overview of confidence intervals. We'll be using our understanding of probability to understand what a confidence interval is, and then show how they're calculated. As we go through this video, we'll first lay out the concept of confidence intervals and provide the justification for them from probability theory. Then we'll look at how confidence intervals are constructed, both for estimates of means and estimates of proportions. So when do we use confidence intervals? Confidence intervals are used when we want to know a population parameter but cannot observe that parameter directly. So instead, we're forced to take a sample and then use the sample to estimate the parameter. Because samples aren't guaranteed to be perfectly representative, that means that there is a margin of error in our estimate. Confidence intervals are what we use to take that margin of error into account. Remember though, we now live in a world of big data. That means that there are some cases where we can actually observe the entire population we're interested in. In that case, we don't need margins of error. However, there are definitely still times when it is either expensive or impossible to observe an entire population. So we have to use sample data. As one example, we can't actually observe the mean liver size of the population of human beings without measuring everyone's liver, which is clearly practically impossible, also wildly unethical depending on the method you choose. So instead, we would take a sample from observing cadavers or perhaps using ultrasound or similar less invasive technology on volunteers. Then we have to infer to the population. In the world of business, there are times that quality control tests are just expensive to perform, so we need to use a sample. Similarly, experiments involving relative effectiveness of advertising often requires a sampling type of approach. So let's start with a simple example. How old am I? And I mean to the day. Think of an answer. Now, how likely do you think it is that you are exactly correct? That is, that you are correct to the day. I think you'll probably admit that odds are you are incorrect. So what could you do to improve the likelihood that you're correct? Well, one obvious method is to guess a range. Right, so rather than guessing 39 years and 124 days, you could say somewhere between 38 and 42 years old. Or if you want to be more certain you get the right answer in your range, you could widen the range, suggesting 35 to 45 or 30 to 50, or in the extreme case, 0 to 120. Another option for improving the likelihood that you are correct is to gather more information. My CV doesn't list my birthday, but you can make a guess from my graduation year how old I am, or you could use the fact that I have 4 kids, and so on. The more information you have, and the more likely you are to come up with a reasonable range, and that's especially true if the information is internally consistent. In effect, each piece of information confirms the suspicions from the other pieces you have, making you more confident in your answer. What a confidence interval is an estimation range for a population parameter based on a sample statistic. In effect, you take the sample statistic and then account for the margin of error, remembering that the sample probably isn't exactly like the population. Now, this margin of error doesn't come from nowhere. Instead, we use our knowledge of probability to construct a reasonable margin of error based on the underlying distribution of that sample statistic. Okay, that last sentence was a mouthful, so let's look at a simple example. Suppose we're trying to estimate what the mean of a die roll on a standard 6-sided die is. One thing we can do is to take a sample, roll the die 30 times, calculate the mean for the sample. Of course, we know that there's randomness involved, so this process isn't going to be perfect. There's going to be a margin of error. However, we can use our knowledge of the distribution of means to figure out what margin of error is appropriate. In this case, we can use our knowledge of statistics to arrive at these facts. First, we know what the true average is. That is, the expected value for a fair die is 3.5. However, if you roll a die 30 times and average together the rolls, getting exactly 3.5 is pretty rare. However, 25% of the time you'll be within 0.1 of that, so a range of 3.4 to 3.6. 58% of the time, our estimate will be within 0.25 of that true average, so 3.25 to 3.75. 90% of the time will be within 0.5 of 3.5. And 99.9% of the time, our estimate will be within 1 of 3.5, which is to say it's extremely rare to get an average for 30 die rolls that falls outside of 2.5 to 4.5. What confidence intervals do then is reverse this process I just did. So with the die, we have the advantage of knowing the true mean, so we recognize the sample mean is going to deviate a bit because of randomness. In many cases, though, we don't know what the true mean is. That's what we're trying to figure out. But it's still true that the sample mean is going to deviate from that true mean because of randomness. So we just reverse the previous logic. If we know that the sample mean will be within a particular range of the true mean, it follows that the true mean is within that range of the sample mean. So we can start with the sample mean, use our knowledge of probability to figure out what the range is going to be, and then we know the probability that the true mean would fall within that range. So here's an example. Suppose our sample mean from the die rolls is 3. Now we know from the distribution that the estimate is going to be within 0.1 of the true mean about 25% of the time. So we can say that we are 25% confident that the true mean, which we denote by the Greek letter mu, it looks kind of like a U with a tail on the front. So this Greek letter mu, the true mean, is in the range 2.9 to 3.1. Now, if we want to do this in general, we have to know the probability distribution, so we can find the appropriate range for a specific confidence level. So let's turn to that question, the question of distributions. Now, that question, I have good news. There are these things called central limit theorems. There are several versions of them, but the conclusion of them is all basically the same. That is, if you draw samples from a distribution, you take the sample mean. The sample means are going to be normally distributed. They'll have that typical bell curve shape, regardless what the original distribution of the data was, as long as the samples are large enough. Now, how big is large enough? That's where things get tricky because it really does depend. In general, if we're dealing with a symmetric data distribution, then the sample size of about 10 to 20 is going to be sufficient. If the original data distribution is not symmetric, you'll need about 30 or more. As a result of this, what we're going to do is treat samples of 30 or more a little bit differently than we do smaller samples. So let's look at an example. To create this histogram, I had Excel draw 100 random numbers from a uniform distribution. This is a very flat distribution. Outliers are literally impossible. As a result, the excess kurtosis is quite negative. For this sample, it's about minus 1.31. Right, so this is definitely not normal. What happens, though, if we draw 100 samples of 30 each, and then look at the histogram for the means? And this is the result. The kurtosis moves basically to 0. It's consistent with the normal distribution. Visually, the distribution looks basically normal as well. In effect, what's happening is that the averaging process is pushing all the observations toward the center. Outliers are getting watered down. Here we don't have strict outliers, but we still have the edges, the zeros and the ones, those close to that. Right, so the sample means are going to be pretty close, right, to the true mean most of the time. How about this Poisson distribution? Here the distribution does look Bell-ish, except that it's skewed right by these extremely large values and a lack of extremely small values. In this sample, if you calculate the skew, it's about 0.8, so it's not terrible, but visually we can definitely see the distribution is not a normal symmetric bell curve shape. So what happens if we take samples of 30 from this distribution and then show the histogram of the sample means? Well, this. You get a beautiful bell shape, approximately normal, and the skewness falls to basically 0. Next, consider a problem of proportions. That is where we're trying to figure out what percentage of a population has a particular trait. Here what I've done, I've just graphed the true probabilities of getting a certain percentage of heads from 10 coin flips So it's a very small sample here. It's only 10. I've superimposed on that the graph of the normal distribution with the appropriate mean and standard deviation here, so it'd be centered and would be the right width. I think it's pretty obvious visually. The two look very, very similar. So when we're dealing with proportions, we can also use the normal distribution. It's going to be really close. And in this case, it also doesn't take enormous sample sizes to get us close enough for the normal distribution to be useful. So what we've just shown is that the normal distribution is what we can typically use to figure out our confidence intervals. This is good news, since the normal distribution is well understood. It's built into any statistical software, including Excel, which is what our class uses. But let's go case by case through some different situations you'll find. First, if you're estimating a confidence interval for a population mean, you can use the normal distribution in two cases. One is if you have a large sample. The other is if the population standard deviation is known and you believe the original data distribution is approximately normal. In that case, normality kicks in for sample means, even if you have really small sample sizes. Now, what if you have a small sample that is fewer than 30 observations, but have to estimate the standard deviation? In that case, you'll have to use something called Student's t-distribution. Student's t-distribution is a bell-shaped distribution, but it has fatter tails than the normal distribution. That helps account for the additional uncertainty that's created by the fact that we're estimating the standard deviation now. Now, if you're calculating a confidence interval for a proportion, you can use the normal distribution as long as you have a large enough sample, defined here by having at least 5 successes and at least 5 failures in that sample. So you might only have a sample size of 10, as say with the coin flips. Now, if you don't have at least 5 of each, then you do need to use something called the binomial distribution, or you need to go out and gather more data until you get at least 5 of each. Now, in our course, we're not going to deal with binomial distribution, so I'll just assume that our sample size is large enough. So, having laid the probability groundwork, how do you actually calculate a confidence interval? It's a 5-step process. First, remember, our goal is to estimate a population parameter based on a sample. For example, we may want to know the defect rate, a proportion, or may want to know the mean approval rating for a store based on a sample of customer surveys. So here are the steps. First, gather a relevant representative sample. Second, calculate the sample statistic, either the mean or the proportion. Third, decide on the desired confidence level. Fourth, calculate the margin of error. And finally, calculate the confidence interval. Let's look at each step in a little more detail. Step 1. Gather a relevant sample. The first module in the course discussed this in more detail, so just a brief reminder, you want a method that gives a representative sample. Options here would include a simple random sample, a systematic sample, a stratified sample, or a cluster sample. Which is best definitely depends on the situation and the cost of administering whatever sample it is. In step 2, we calculate the sample statistic based on the sample we've gathered. There are 2 we'll be working with, either the sample mean, which we calculate as kind of a standard average, sum up the observations, divide by the number of observations, or we may be interested in the sample proportion, which is a lot like calculating the simple probability of finding a trait. So you take the number of observations that have that trait, we call these successes, and then divide by the total number of observations. These sample statistics are what we would call point estimates, and will be at the center of our confidence interval. Now we have our point estimate in hand, so we need to figure out what the range around it should be. That's where step 3 comes in. We need to choose our confidence level. Roughly speaking, a 90% confidence interval means that we're 90% sure that the population parameter, that is either the mean or the proportion, is in this interval. Now, more precisely what it means is that if this sample is representative of the population, then 90% of similar sized samples from the population will have a statistic in this interval. However, this precise definition is pretty unintuitive, so it's more common to hear that more intuitive, there's a 90% chance the population parameter is in the interval. Now, one common confusion, though, on this point. Many people confuse a confidence interval with what we call a prediction interval. A confidence level is about the location of, for example, the mean or the proportion. It is not about the location of individual data points. So interpreting this 90% to mean that 90% of the data is in this range, or that there's a 90% chance that a particular observation is in this range, is incorrect. The confidence interval is really more about the probability of catching the mean in our interval. One distinction that I like to make in analytics is between using the computer and being the human. Much of what we teach and talk about in the world of statistics or analytics now are things that computers are built to do, and confidence intervals are no exception. However, there is an extremely important be the human task here. You, as the analyst, have to choose the confidence level. And this is based on a trade-off between precision and accuracy. So on the one hand, a low confidence level, something like 50%, will give you a very narrow range for your interval, so you get very precise estimates. However, the probability of it being accurate is also pretty low, only 50%. A 99% confidence interval, on the other hand, is very likely to catch the true value of the mean, for example, but it does that by being very wide. So it's a matter of judgment which you should use. Now, if you're new to these ideas, this isn't really very helpful. It sounds like you can just pick any number between 0% and 100%. Well, that is strictly true. It's also true that there are conventions that we use. So most often you'll see 95% as the typical confidence level, though you do sometimes see confidence levels drop a bit lower, like 90% or so, or go a bit higher, say around 99%. So what's the confidence level then used for? Well, in the next step, what the confidence level is going to do, the confidence level we choose is going to provide a multiplier that will affect our margin of error. The relationship is fairly simple. That is that the higher our confidence level goes, the larger the multiplier has to be. And so the larger the margin of error is going to be. Put another way, we need a big margin of error if we want to be 99% sure that we catch the mean. Now we'll save how we find the exact multiplier for a little bit later, but for now just know that it will rely both on the confidence level we choose and the relevant distribution, either a normal distribution or the student's t-distribution. The fourth step then is to calculate the margin of error. This is something that can easily be done in Excel using confidence.norm or confidence.t. But I want to talk about how you do this by hand so we can see how the various elements interact with the size of the margin of error. So the general formula is that the margin of error is plus or minus the multiplier, which is typically called z star or t star. This multiplier reflects both the relevant distribution, z in the case of normal, t in the case of student's t-distribution, and also the chosen confidence level. Then this multiplier is multiplied by the standard deviation, either one that we know somehow, or one that we estimate based on the sample we have. Finally, we divide this by the square root of the number of observations in the sample. This ratio of that standard deviation divided by the square root of the sample size is what we call the standard error. So another way of expressing this margin of error is to say that the margin of error is a multiplier multiplied by the standard error. A couple of observations about this standard error. If the standard deviation of your data goes up, the standard error, and therefore the margin of error, will get bigger. This reflects the fact that the data you have shows a great deal of variety, maybe even outliers, and that creates uncertainty about the mean, so we need a big margin of error to be sure that we catch it. Second, if your sample size goes up, then the standard error and the margin of error are going to drop. This reflects the fact that as you have more data, you're going to get a more accurate estimate that is less influenced by things like outliers. So how do we find out the right multiplier? Now, in reality, we use software. However, if we want to go old school, we use a t-table. A t-table has rows for various degrees of freedom, I'll describe that in a minute, and columns for various confidence levels. In the t-tables that I would use, confidence levels tend to be listed at the very bottom, so I would use that to determine which column I need to look in. To find the correct row, then, I either use the z-row, which is based on a normal distribution, if I'm working with proportions or have large enough samples to use the normal, or you would select the row for the sample size minus 1. That's what we call the degree of freedom. Now these numbered rows are going to be based on student's t-distribution. Student was the pseudonym of the person who first developed this distribution. William Seeley Gossett, he worked under a pseudonym to prevent revealing that his techniques were being used for quality control for the Guinness Brewing Company, where he was the head brewer. In any case, what you're going to find is that the multiplier is bigger for small samples than for large ones. This reflects the uncertainties involved with estimating that standard deviation. And the multiplier is bigger for higher confidence levels than small ones. Again, reflecting that widening the interval is going to increase the likelihood of catching what is actually true. So just a few examples of common multipliers based on the normal distribution. A 95% confidence interval has a multiplier of 1.96, so it's approximately 2. 90% has one of 1.645, 99% has one of 2.58 or so. Generally speaking, unless you're dealing with very small sample sizes, if your confidence level is 95%, you're going to use a multiplier somewhere close to 2. This can be useful in helping you look for things that feel a bit off, as error identification is another human task. Another point about the t-table. Technically, even with large samples, if we're estimating the standard deviation, the t-distribution is correct. However, in practice, once the sample size reaches 30 or so, the difference between the two becomes so small that we just use the normal distribution. However, this is, to some degree, really a relic of the age before computers and statistical software were so widely available. After all, multiplying by 1.96 is a lot easier than having to look up the slightly higher t-multiplier. However, with the advent of statistical software, using the t-distribution in this case is not nearly as inconvenient as it once was, so feel free to go ahead and use t anytime that standard deviation is estimated from the sample. Now I want to talk a little about the importance of using the correct degrees of freedom. On this graph, I show the t-distribution for degrees of freedom of 1. That's what you'd use if your sample size is 2. Degrees of freedom is sample size minus 1. So 2 minus 1 would be 1 in this case. This is the blue line with a fairly low, narrow peak and fatter tails. Meanwhile, if the sample size was 21, the degrees of freedom would be 20. 21 minus 1 gives me the 20. And that leads to the orange line being the distribution. Here, the peak is noticeably higher and wider, and the tails are much, much thinner. This reflects the fact that with more data, the estimate of the standard deviation is going to be better, so we can be more confident within a narrower range. Just as an example, with these numbers, if I used a multiplier of 1, it would give me a 50% confidence interval with the degrees of freedom of 1, but a 70% confidence interval for degrees of freedom of 20. The purpose of this graph is just to show why we would usually switch from students' t-distribution to normal at n equal to 30. This graph shows both what the student's t-distribution is with 29 degrees of freedom. That's what you'd use if you have 30 observations. 30 minus 1, 29. It's 29 degrees of freedom. I have that overlapping here with the normal distribution. The graph looks remarkably similar. That's why traditionally we would just switch to using the normal distribution once we have a sample size of 30 or more. Now that we have our margin of error, calculating the confidence interval is pretty straightforward. You take your sample estimate and you add and subtract that margin of error to get a range. So if your sample mean was 3 and you have a margin of error of 0.7, then the lower end of your range is 3 minus 0.7. And the upper end of the range is 3 plus 0.7. So you end up with a range of 2.3 to 3.7. This problem. Suppose I want to calculate the mean height for a class of 20 students. On the day that I gather the data, though, 2 students are missing. So we have a sample, not the population. As a result, we should need a margin of error. However, in this case, the standard approach is going to create problems. Take a second to think about why that might be. Okay, here's the problem. We only calculate the margin of error because the sample might not look exactly like the population. It's only a small part of the population as a whole. So there might be a difference between the sample statistic and the population parameter that it's estimating. However, if the sample is the population, we know there is no margin of error. We just see the population parameter directly. So what happens if we sample almost, but not quite the population? In this case, our estimated margin of error tends to be too big using standard methods because there just isn't enough population outside of the sample to push that population parameter very far from the sample statistic. So in cases where we sample a lot of the population, we need to account for the fact that so little of the population is outside of the sample. Enter the finite population correction factor. We use this correction whenever we sample more than 5% of the relevant population. Now technically, we can use this anytime the population is of a limited size and you're sampling without replacement. But for less than about 5% of the population, the correction is so small that it makes no practical difference. If you're sampling at least 5% of the population, though, you'll want to correct your margin of error by multiplying it by the square root of the population size minus the sample size divided by the population size minus 1. So if you sample the entire population, the numerator cancels out to 0, so there's no margin of error at all. If you sample, say, 25% of the population, your margin of error gets cut roughly in half once you use this correction factor. If you sample 80% of the population, the margin of error gets divided roughly by 10. Now, turn towards some of the special characteristics of confidence intervals for proportions. The video mentioned earlier that a proportion is the percentage of a population that has a particular trait, like the defect rate for a manufacturing plant being one important one in business. The proportion can be calculated as the number of successes in your sample divided by your sample size. This is the point estimate in this case. Calculating the confidence interval, though, there are a couple of special adjustments we have to make since it's not obvious how to calculate the standard deviation in this case. The standard deviation can be estimated by the proportion times 1 minus the proportion, and then taking the square root of all of that. So if we put this together with the square root of the sample size that's normally the denominator in the standard error, we now get this expression. The square root of the proportion times 1 minus the proportion divided by the sample size. So that would be our standard error, which then we would multiply by a multiplier. Now remember, as long as you have at least 5 successes and at least 5 failures in your sample, you can use the normal distribution to determine that multiplier, which here I denote as z star. Otherwise, you'll have to use the binomial, which that's going to fall outside of the scope of this course. Last topic here. The equations we have here can be rearranged to allow you to choose your margin of error, if you get to choose your sample size. As long as you have the other elements, the desired confidence level, so you can have the right multiplier, a reasonable guess for the standard deviation, and your desired margin of error, you can rearrange the formula for margin of error to determine what sample size is needed for a specific margin of error. Here's the result for both means and proportions. I'm not going to read off these formulas, but I do want to point out a few things in practice. First, you're having to make a guess of the standard deviation. Guess high. For proportions, you need to guess the proportion. In this case, don't guess high. Guess as close to 0.5 as is reasonable. If you have no clue, just guess 0.5. The reason for this is to push toward overestimating the necessary sample size rather than underestimating. In most applications, a margin of error that is small is a good thing. So if we take a sample that's big enough to drive the margin of error lower than we wanted it to be, that's generally not a big problem. Along that same line, always round the result up. There's no reason to expect these formulas to give you a whole number, so you'll need to round. So round up. If you get 37.16, make it 38. Again, this is to help make sure that the margin of error is the size you want or smaller, since larger samples will push down those margins of error. Now, one complication you can run into is that if you calculate using a multiplier from the normal distribution, sometimes you'll get a sample size where a t-distribution would be needed. In that case, you have a couple choices. Either recalculate a few times, trying to find out which degrees of freedom gives you a consistent result by replacing the z here with a t star and using your t-table and all of that. Or you could just choose a sample size of 30, since at that point the normal distribution is valid, and the formula indicated that less than that was perfectly fine. Which is the best option is going to depend on the situation, particularly in how difficult or expensive it is to gather observations for your sample. So a few takeaways. First, don't worry too much about the formulas. Excel or other statistical software can be your calculator. Instead, you need to focus on being the human. So here are your responsibilities in that position, at least at the current state of technology. First, know the difference between a sample and a population and how we should treat each. Don't mechanically calculate confidence intervals if you're working with population data. Second, know when to use the normal distribution versus the t-distribution and how to implement it in whichever software you're using. Third, develop the ability to eyeball for mistakes. This is something that comes with time and experience, but over time you will learn that various rules of thumb, like that the margin of error should be about 2 times the standard error, which should help you identify errors or mistakes whenever they occur.